This is the estimate for beta or beta hat, and this is the normal equation. Welcome back to Honey of Knowledge. This is Ashish Gourav, and you're watching mini lectures on econometrics. If you're new here, this is a series of lectures based on what I have studied as a part of a master's level course in quantitative economics at the Indian Statistical Institute. So, a lot of topics which I cover would be of master's level. If you're new here, it would be prudent enough to subscribe to this channel, and let's get started. In the last lecture, we have introduced the linear algebra analysis of econometrics. We have replaced the normal y is equal to a plus bx plus e with y is equal to x beta plus e. Now this y is equal to x beta plus e can be written in two other forms. You can expand x beta into its constituent betas. Now here betas are essentially the coefficients of the predictors. x1 is just a vector of ones, which means beta 1 is giving you the intercept term, and the rest of the term are basically coefficients on the predictors. So x2 to xk are the values of predictors. So you have k minus 1 predictors, and e is error, as you already know it. Now we can also decompose it into the matrix form, which is actually very powerful for a lot of analysis which we will be doing in this mini lecture. So y has t observations. So y1 to yt gives you a vector of y values. X beta can be written as x into beta, where beta is your vector having k cross 1 dimension, because I have beta 1 to beta k, and this x matrix is of t cross k dimensions. So when you multiply x with beta, you have a t cross 1 matrix, and it is the same as y vector, and that is pretty obvious in nature because y is equal to x beta plus e, so the dimension of y should be the same as x beta and e already has t cross 1 dimension because e will be composed of t errors. This is a recap of what we have achieved in the previous lecture. So now let's try to find out beta. But before we find out beta, we need to understand few assumptions of this model. This model is known as classical linear regression model, and there are 3-4 assumptions here. So let's go at those assumptions one by one. The first assumption is of linearity, which is pretty obvious because y is equal to x beta plus e is a linear equation. But we need to be careful here because a lot of times there could be correlation between y and x, but we cannot represent the data as y is equal to x beta plus e. So that is why this assumption is important when you are trying to model y and x. Second assumption is expectation of error is 0, or expectation of the error vector is 0, which means that this is also quite understandable, and we are just using the vector notation to make our analysis simpler. The third assumption says that all the EIs or the error values are IID, independent and identically distributed, having a mean of 0 and a variance of sigma square. This gives rise to an interesting result. As you can recall, you can calculate variances using expectation for scalar quantities, which means for x, y, or any random variable, you can have an expectation and a variance based on that expectation. Now, you can also have a variance for a vector quantity. Vector quantity meaning a vector of error values, or simply E. So how do you calculate the variance for that? Essentially, we do not call it variance, we call it variance covariance matrix. And as we know from the previous assumption that expectation of E is 0, we can simply write the variance covariance matrix for E as expectation of EE transpose. This is E and this is E transpose. Now E has a dimension of T cross 1. This has a dimension of T cross 1, and obviously as you're making a transpose, it will have a dimension of 1 cross T. So the moment you multiply them, you will have a dimension of T cross T, which will give you a square matrix. So this is the variance covariance matrix for error values, or E. This is what you will get if you multiply E transpose. And remember, we need to find the expectation of this, because the variance covariance matrix is expectation of EE transpose. And as we have mentioned that all the errors are independent and identically distributed with zero mean and sigma square variance, it means that if we take the expectation inside these quantities, the off diagonal elements E1, E2, E2, E1, ET, E1, E2, E2, these values essentially are trying to find the variance between these two error terms, and as they are independently distributed, they will go to zero if you get expectation inside. But the moment you take the expectation inside for the diagonal elements, it will return you the variance, which is sigma square. So expectation of EE transpose variance covariance matrix is equal to expectation of this quantity, because E is a vector and E transpose will become this kind of a matrix. If you multiply them and you remove off the off diagonal elements, you will get this square matrix. Now the diagonal elements are sigma square, have the same value, so you can represent this simply as sigma square identity matrix of order T. So this is sigma square into identity matrix of order T. Now this assumption is giving you this result, and this is known as homoscedasticity, which means the variance covariance matrix is of this nature. This will be relaxed in a future lecture, and we will see how it affects our econometric analysis. So I'll just go to the next assumption. The last assumption states that X is non-stochastic and determinant of X transpose X is not equal to 0. Now let's understand this one by one. What is X? X is a matrix of the predictors. When I say it is non-stochastic, it means that for our purpose, it's not changing. You can take this as simply not changing. Non-stochastic meaning not changing. I mean, if you go into the definition of stochastic, it will be a difficult thing for a small lecture, and we will not be getting into the technicalities of stochastic nature. So for our purposes, let's just think of X as not changing, and we will be trying to relax this assumption in a future lecture and see what happens if we do that. Determinant of X transpose X is not equal to 0 is immensely critical, and we will see this just in a matter of time. Why this is important? Because if this is not satisfied, a very vital aspect of our analysis will not go through. Let's proceed to the estimation of beta. To estimate the value of beta, we need to minimize the sum of squared errors, the usual thing which we did in the simple case too. And in this case, what is error? Error E is equal to Y minus capital X beta. So we need to minimize the sum of squared errors. But there is a catch. This is not a scalar quantity. This E is a T cross 1 matrix or a vector. So this also is T cross 1. So how do you minimize the sum of squared errors? which is required by the least squares criterion. So if you recall a bit of linear algebra, E transpose into E would give you a scalar quantity. Now you need to understand why. E has a dimension of t cross 1. So the transpose of E would have a dimension of 1 cross t. So if you multiply them, it will have a dimension of 1 cross 1, which is a scalar quantity. So if I find E transpose E, it will give me a scalar quantity. Now what is that scalar quantity? This is E transpose. This is E. Let's find out E transpose E. E transpose E is equal to E1 into E1 plus E2 into E2 dot plus ET into ET, because that is how you multiply two matrices, which will give you, lo and behold, sum of squared errors. And this is what we need to minimize, which means we need to minimize this, where E is this quantity. So I'll come again. E is this. E transpose E is sum of squared errors, and this is the quantity which we need to minimize, or rather this. So let's proceed with minimizing E transpose E, where E is y minus x beta. We can represent E transpose E as this expression, and if we take the transpose inside the bracket, we will get this. The reason being, CD transpose is equal to D transpose C transpose, which means if you get transpose inside, you have to flip it around when you're multiplying two matrices. So over here also, transpose gets inside Y comfortably, but when it gets inside here, there are two matrices, so you need to flip it around. This is equal to this, and if you look at these two expressions, they are actually the same. This is transpose of this, and this are scalar quantities. Why? This guy over here is B transpose, and B is of dimension k cross 1. So this is of dimension 1 cross k. X is of dimension t cross k. So this is of dimension k cross t. And Y is of dimension t cross 1. So this is same, 1 cross 1. You can also look for the dimension of this. This is of dimension k cross 1. This is of dimension t cross k, and this is of dimension 1 cross t. So again, same, you have 1 cross 1. So essentially these two guys are same. So we will club them and simplify this expression, as these two quantities are scalar and transpose of each other. Now we have got a simplified version of E transpose E, and we need to minimize this. And in order to minimize this, we will need to find the first order conditions. Minimize. For that, we need to find the first order conditions. So let's proceed to the first order conditions. To minimize this, or to find the first order condition, you need to differentiate this and put to 0. Now obviously this expression is a kind of matrix expression, and it involves a lot of matrices, so you cannot differentiate it in a normal way. So we'll need to resort to how to differentiate matrices, but I will not go through those steps because that is not the point of this lecture. So I'll reserve those segments for linear algebra lectures. So in linear algebra lectures, I may go on to tell you how to differentiate when you have matrices in your expression. So let's skip to the next steps. Differentiation is done with respect to beta, and this has no beta. Only these two terms will give you some non-zero quantity. So if you differentiate this quantity with respect to beta to find out the first order condition, you will be getting, if you compare these two expressions, this was having no beta, so it goes to 0. This had a beta transpose that vanishes away, and this had a beta transpose beta, so beta transpose vanishes away. And as you have beta transpose into beta, so it will definitely give you a kind of a second degree expression. That's why a 2 appears here. That is a kind of a rough idea I can give you at this point of time, and more on the differentiation part in the linear algebra lectures. So if we have reached this first order condition, this is also known as normal equation. So let's simplify this normal equation further. After this stage, you need to find out beta. But remember, we are estimating beta. So we will not get beta, we will get beta hat. So this is the normal equation which you will find out in standard textbooks or in any kind of material on econometrics. So if we need to find out beta hat, we need to get rid of this quantity. Let's multiply this with x transpose x inverse. So if we multiply this with x transpose x inverse in this side, this will vanish away because inverse of a matrix into that matrix is identity matrix. But we need to multiply that inverse matrix here also to the left of this quantity. So we will be getting beta hat is equal to x transpose x inverse x transpose y. Now if you remember our assumption on the determinant of x transpose x, it had to be non-zero, and now you can understand why. If the determinant of x transpose x is not non-zero, then you cannot find the inverse of x transpose x, and if you cannot find the inverse of x transpose x, then you cannot find out the beta hat value or the estimate for beta. Hence, this is the estimate for beta or beta hat, and this is the normal equation which helped you to get the estimate for beta or beta hat, which is x transpose x inverse multiplied by x transpose into y. This is it for this lecture on econometrics, and I will be adding more lectures, or rather mini lectures, on the course I have done at the Indian Statistical Institute for my masters in quantitative economics. So do not forget to keep checking this channel, and a better way would be to subscribe and press the bell icon. And if you like this video, why don't you give it a thumbs up so that I know it. And you can watch my other videos playing around here by clicking on these video links. Bye bye.